All right, let's get back into pointers. We are getting very close to the end of the semester. We just have today and Wednesday, and then next Monday we'll have the review. And wow, the exam is already like a week and a half. That came fast. Just like for the midterm, we'll have a review session before the final. It'll include everything in the class, but it'll be weighted towards the second half since we already had a midterm on the first half. And today's homework will be the last homework. I did make a homework, I just didn't put it up yet. So yeah, this will be the last homework. This is the 24th homework, even though it's labeled homework 25 because it's for lecture 25. So the last homework's up. Cogen 3 is up as well. As I said, it's just going to be the same as Cogen 1 and 2, especially 2, except there's different functions to implement. It's the pointer functions, which you can't see. Okay, now you can see. So here we're here in the 25th lecture. Homework 25 is up. We'll have one more lecture on pointers, although we may finish everything today on pointers, so we can leave this as kind of open review or covering whatever you'd like to cover. Then we have a review for the final. The final is just in a week and a half. Project deadline is a little after that. You'll have more time to work on that. Remember, this is the final project for all resubmissions and for Cogen 3. Let me know if you have Cogen 3 in early, and I'll at some point probably do a sort of mass grading of Cogen 3 before this deadline, because you won't be able to resubmit after 4/28, right? So it's the deadline. Basically, you can't get a late point for Cogen 3 as the consequence of this. So make sure you submit it early if you want like feedback on Cogen 3. Yeah. For Cogen 3? I'll get them up this week. So today was the day I was supposed to release it. Yeah, I'll get these up soon. I have them designed. I just need to publish them. But as always, you should be writing your own test cases. So you shouldn't be depending on me for test cases. That's why I only give you half of them. Describe the rest. They'll never be released, but they're described, so you can test it yourself, right? If you go work for a company, they're not going to sort of spoon feed you everything exactly that you need to do, and then if it doesn't pass the test, you can't just be like, complain, give me more tests, right? You'll just get fired probably. So write your own test cases for the problem. All right, any questions on pointers, compilers, Cogen 2, Cogen 1? Yeah. All resubmissions, yeah. So this is described down here in the late policy summary and in the due dates. So this is the end. This is everything. Everything will be due here, and then by this point, after this date, basically, probably almost the next day, we'll have all your grades at this point. All the grades will be final at this point. Some people have already reached about a makeup exam. Let me know. If you have an excused reason, let me know on EdStem with a private message. I'll try to make one final exam period like I did last time. It'll be a different test. Yeah. Yeah, that's a good question. 2 hours. Yeah, that's pretty early. Let me make a note to make sure I time the exam properly. So the midterm was an hour and 20. We had like an hour, right? Hour and 10 minutes. Will need to be a little longer. It counts for more. It includes more content. So if it's 2 hours, that's maybe like 8 or something. Let me make a reminder for myself. Yeah. Yeah. So if I change the date or the time, that should be fine. I think you can just ask them and send and CC me, and I can confirm. All right, so let me make a reminder to do this. Yeah, I guess we start at 8 a.m., then that's like, what's 50% more of an hour? That's like 90 minutes, so that would be about right. How does 8 a.m. sound? 8 a.m. a little better? All right. So let's say sort of unofficially now, 8 a.m. instead. Yeah, that's very early. Maybe 8:05, so it's an hour and 45 minutes. All right, but let me, remind me again on Wednesday if I haven't changed this. And I'll, actually I can go into SAS and change the time. I think I have to set the time, so. And I don't think I've done that yet, so. All right, other questions on the last couple of weeks, just the last couple of weeks? Wow, that went fast. All right, let's go over homework 24. The question was, if we have a variable x that is an offset negative 24 from the base pointer, write x86-64 assembly that will result in the address of x being stored in register RAX. All right, let me get... Okay, let me get this, just getting my Emacs set up. Okay, so how do we get the address of the variable x? What is the address of variable x? So if it has an offset of negative 24 from the base pointer, what's the address? RBP minus 24. So sort of write this in a kind of pseudocode. The address of x is whatever the value of RBP is minus 24. So how do we express that in x86 assembly? Say again? Okay, so one way to do this is using this addressing mode. So if I, for instance, do this, if I do move this addressing mode negative 24 offset from RBP to RAX, what will RAX hold after this instruction? The value of x, right? It'll be the value of the memory location that's associated with x. So it's not going to give me the address of x. How can I express getting the address of x? So this addressing mode builds in the logic to compute the address, but then does a load from that memory address. So this loads the value of x. So how can I load the address of x? Yeah. Okay, so you load whatever's in RBP. So we take the value of RBP, which is an address in memory. And in order to do arithmetic on it, we can only do one arithmetic instruction at a time here. So first, we copy this to a new register. Now, we could have just subtracted negative 24 from RBP. Why should we not do that? You're going to blow away. Well, yeah, that's wrong, right? That's wrong. But okay, so let's say we actually successfully subtract 24. Why would we not want to do this? You change RBP. I guess you could generate code that then subtracts it afterwards and then it would restore it. You could probably actually do that if you wanted. I find that a little confusing. So instead, we take RBP, put it into a separate register so we don't touch RBP, and then we do our addition or subtraction. So this will subtract or add negative 24 to RAX, which previously held RBP. And now RAX holds the address of X. Yeah? That's a good question. I assume it's like this. Whatever this would be like 1 plus 8 or something. I assume it's like that. I actually don't know. An AT&T x86 syntax. Gotta be the way to do it. I'm assuming it's like that. Yeah, I don't know. None of these first results say it. But my guess is it's like that. Yeah, I can't find it. But if you find it, let me know. But I assume it's like that. I actually don't know. Okay, any other question? Any questions on?
Yeah,
It is like that. Okay. Yeah.
So RAX is holding the address of X right now, right? And this is with X.
Yes. Good. Well, yeah. We'll get the value of X. That's right. Yeah. So good question. So now that we have a register that holds an address, how can we load and store from that address? Well, we use the same syntax that we use for RBP. Wrapping it in parentheses is like star in C. It's dereference. So if I wrap RAX in parentheses and store it into some other register like RBX, this will get the value of X. Not the address of X, the value of X. RAX holds the address of X right now. This indicates to the processor to use the addressing mode, where we get the address from a register, load it, and store it into the destination register. By the same token, I can store into that address by making it the destination of the move instruction. This is what we saw last time when we, and I'll go over this again, but this is what we saw last time when we want to dereference a variable, and this is what we'll see today when we want to assign to a dereferenced variable. Questions on this? So this is equivalent to star X equals RBX, and this is equivalent to RBX equals star X in a C-like pseudocode. Yeah. You can absolutely address an address out of the stack frame. So you, as the programmer, you have the. Remember we talked about processes. The operating system gives you this vast virtual address space with the illusion that you have complete control over memory, over RAM. So you can, as the C programmer, you can write a program that addresses anything in that space. Now, there are parts of that space that are reserved for the operating system, for operating system stuff. And so that's why you'll get a seg fault if you try to dereference null, because that part is reserved. There's also more modern, well, I guess it's several decades at this point, but more modern memory protections where the operating system can mark certain parts of memory as read-only or execute-only or write-only. And that's to protect against, say, rewriting code accidentally or executing the stack space. So there's a classic architecture security protection called write XOR execute. So write or execute. You can only do one or the other with memory that's marked as write or execute. But yes, you can address whatever you like. The malloc works on top of the operating system. So once you're allocated the memory, malloc is a user space library. You could rewrite your own version of malloc. You don't have to use the malloc given to you by the system. You could allocate memory on your own and keep track. And I think an operating system class should go over malloc, how malloc works. But it just, keeps track of what memory you've asked for allocation before. All right, other questions on this homework assignment? Yeah. That does which exact thing?
like loads an offset from
You mean the address of it?
yeah, like
Not this, right?
or yeah, not that. Like what's posted in the homework, but like in a single
There may be. There may be. I don't know what it is. If you can find it, let me know. There very well may be. Intel, or the AMD or the Intel x86 platform is 6 CISC. It has lots of very special case instructions. There are lots and lots of ways to write the same program. But yeah, I'd be curious to know if there may be an instruction to do that. But I don't know it. All right, other questions on the homework, on the content so far, programming projects, logistics?
yeah, the instructions will LEA, low effective address.
Let's see. Computes the effective address of the second operand. Oh yeah, and stores it in the first operand destination. So that sounds right. Probably it's that. This actually tells you the pseudocode for it. Probably. Use that if you like, or do it the hard way.
I remember seeing that. It was used for like not.
Give me 1 second. All right, so here's our stack. Contains our return address, so this is the stack frame for main. That return address goes to the caller of main, which is the C runtime. We've got our old RBP, and now, independent of any call saved registers or anything, we've got our local variables. So last time I gave these addresses to the memory locations, to the memory slots. Okay, and these are our local variables. We have variable A, B, X, Y, T1, T2, T3. What's the address of RBP after the prologue of this function is executed? What's that? Actually 112. 112 is it. So remember the prologue, you push the old base pointer and then set the new base pointer to be the top of the stack. So that's why the first variable will always have a non-zero offset from RBP. These are all the offsets from RBP for our local variables. Okay, so here's our setup. RBP is here. And let's go through and just execute these again. So when I assign X to 8, how does our state change? How does the state of our stack change? Memory address associated with X gets assigned the value 8. Same with Y, gets assigned the value Y. What about the next instruction? T1 equals ampersand or address of X. How does the state of memory change? T1 equals 88. Why 88? That's the address of X. It's RBP, which is 112 minus 24. which is 88. All right, good. So T1 equals star or dereference of T1. How does T1 change? Say again, T2 equals 8. Okay, so we're assigning T2, this memory location. So this is the memory location that's going to be the destination of the store. The source of it is related to T1, but we're doing star T1. Star T1 dereferences T1. So what that means is it takes whatever the value of T1 is, which is 88, and then uses that as the load. So this address, so it's not actually copying 88 into T2. It's copying whatever value is at the address 88. That's the essence of what a pointer is. A pointer is a memory location that stores a number, and that number is used as an address for loads and stores. So that's why the machine doesn't need to know what type of values there are in memory. It completely comes down to what operation we use. So if we use star or dereference on a variable, it doesn't really matter what that variable contains. It's going to be used as an address, even if that address is 0 and you get a seg fault or a null pointer error. So this instruction, T1 equals star T1, first looks up the address of T1, records it in a register, and then loads from that register. So it loads the value at address 88, storing 8, which is the value of X, storing it in T2. And finally, we've got star T1. All right, so let me back up and let's go over what the actual assembly looks like for dereferencing a pointer. Okay, so this is sort of review at the end of last time. This is what we saw last time. This is how you, and for homework as well, we just saw this for homework. This is how you take a value in a register and treat it as an address. So instead of loading from a fixed address in memory, we're loading from the address stored in RAX. So for instance, if RAX holds address 88, what value will RBX have in this machine state? So RAX holds 88 and we run this instruction. What's the value of RBX? What's that? Would it be, yeah, so it would be 8. It would be 8. Because, what's that?
In that previous video, if it said T2 equals star X, would it just try to find whatever's at the address of C?
Yes, yeah. So if we said T2 equals star X, it'll take 8. And so for instance, if RAX instead here, if I can change the example here, if RAX were 8, and we ran this instruction, what would the value of RBX be?
Would it be whatever's inside the data?
It's whatever is in address 8. So it's not depicted here. It would be somewhere lower down the stack or more likely in a heap or even in the code segment. It would be somewhere else in memory that does not correspond or may not correspond to a local variable. Because to the machine, the whole address space is just memory. It's just a giant array of addresses. And it's up to you as the programmer to stick to your own usage of that. So if you defined this area to be the function local variables, you should only generate assembly code or write C code that will access those variables. So if you accidentally dereference X or do some pointer arithmetic that, say, puts it in a different memory location, well, that's kind of on you. It's just the machine is going to do exactly what you ask it to do. Yeah, is there another question? So, yeah. It depends on what the address is. So you get a segmentation fault because you're trying to read memory addresses that the machine, that the operating system and the hardware has prohibited you from reading or writing. So if you happen to be just off by 8 bytes, you might read memory that you have access to, and the program will just continue to run. You won't get a seg fault. You won't get any hardware or operating system protection against that, at least by default with C. So this is, as I mentioned before, this is the source of stack smashing attacks, the kind of classic buffer overflow and other stack overflow stack smashing and other buffer overflow related attacks, if I have an array here, if B is an array, then B0 is this location, B1 is this location. If I've only allocated 2 spots for it, but I access B3 or B4, B4 is the return address. So if I've written a program that allows for address offset 4 in B, array element 4 in B, to rewrite this, then someone who's using your program may be able to rewrite the return address. And if they're very clever, they may be able to rewrite other addresses to hold code and then branch to those addresses and start executing those addresses. So that's the classic stack smashing attack. This understanding how the calling convention works, how memory is laid out, how the compiler or the operating system work together to store memory locations and implement arrays and all sorts of other language features. The understanding of how those are implemented, the consequence of that leads to these kinds of security attacks. Now, there are all sorts of protections against this these days. I think you can take like a malware analysis class here to learn about these mitigations or just read about it online. But yeah, this is still how C programs and other system software is implemented at the machine level. So yeah, remember, the type system is just for the compiler to try to check on your behalf whether you've used your variables in the way that you've told it you're going to use it. But at the machine level, there's no typing. Each of these addresses is just a 64-bit sequence of bytes. And whatever instructions you tell the machine to do, it's going to do that. It's going to do that on your behalf. So it's up to you or the programming language implementer to make sure that it only operates in the way that you expect. So remember, the definition of a bug, my definition of a bug, it's not that the machine does something wrong. It's that the machine does something that you didn't expect. You think the machine is going to do one thing, but the machine does another. So if you wrote C code or string processing code that doesn't check the bounds of arrays, you thought that the program would only behave correctly. You thought that it would always return to the correct address. But in fact, the program will actually return to an attacker-controlled address. So that's why that definition of the bug matches there, where the actual program behavior working exactly as intended doesn't match what you thought it's supposed to do. So it's specification versus implementation. That's, to me, what a bug really is. It's not that the machine does something wrong. It's that we misunderstand what the machine is going to do. So yeah, if you tell it to dereference 8x and get the address 8, machine's going to do it, for better or worse. It's going to do it. And if it's to an address that you have access to, then the program will just continue. And that's sometimes called a logic error. It's much harder to debug those because you don't get any signal about an error. You get an output. The program doesn't crash. So if you're just relying on crashes, you may still have bugs in your program. That is, misunderstandings of what it's supposed to be doing. All right, so that's how the accessing a dereference variable will be. This was the kind of pseudocode. You first get the value of the deref variable. So in our case, we were T2, so the operation we were trying to compile here is T2 equals star T1. We're trying to dereference T1. The way we do it is we first get the value of the deref variable, which is 88. So T1 is 88. We get that value stored in a register. And then we get the value of the memory at that address. We load from that address. And we can use this indirect move to do that at the machine level. And then finally, we take the value that we got from the address, 88. In this case, it's also x. T1 points to x, so it's the value of x. And then we store that into the destination, which is T2. So here's what that assembly code looks like. So first, we take the value of T1 and we store it into RAX. So what's the value of T1 here? 88. So we take 88. This is how you load from the memory location associated with T1, and that's how we load it into RAX. So this is where this gets a little tricky because RBP is also a pointer. It's like it's as if RBP is an array that you're indexing into. So it can be tricky to think about the fact that T1 is an address as well. T1 has its own memory location, -40. But the value of it is also a memory address. That's what makes pointers confusing, especially at the machine level, because all variables are in memory locations and they have memory addresses associated with them. But what makes a pointer is that we start taking these addresses, which we use to access memory, and we start putting those addresses in the values. We put those addresses into the memory values themselves. That's what causes a pointer. So if you've ever been confused by pointers, this may be a way to help you make it a little more tangible, a little more physical as to what pointers are doing. So if you could also have, say, multiple levels of pointers. So we can have a double pointer, for instance. If I have some memory location here, -40, -40 points to this memory location. That contains the value 88, which points to this memory location, etc. So has anyone dealt with double pointers in C?
Yeah.
Oh.
That's how you make the 2D array.
Oh, okay, yeah, good point. Okay, yeah, okay. So good. And triple pointers? Anyone deal with triple pointers? Function pointers? Anyone have to deal with function pointers? Oh, okay, good. A lot of people do function pointers. Function pointers are also really, really annoying, but those have been kind of made easy by, say, C++ or objects, which are basically just function pointers. Okay, so that's what this instruction does. It takes the value of T1. The value of T1 can be accessed from an offset of RBP. That's 88, and it stores it into RAX. So now RAX holds the value of T1. Holds the value of T1. Okay, so the next instruction, this is where we do effectively the pointer part. This is where we dereference the pointer. We take the value of RAX and dereference it. We look up that address. We load from the address given by RAX. Remember, if we didn't have these parentheses, we would just copy the value of RAX to RBX. Here instead, we're loading from memory. We're loading from a memory address. Where's that memory address? Given that memory address is in RAX, the value of RAX. So we take that memory address and load, so it's memory address 88, and we load that value into RBX. So RBX will now hold the value 8, which is the value of X, right? Because T1 is a pointer to X. So if you dereference it, you're going to get the value of X. This is at the machine level how pointers work. This is why pointers operate the way they do. Because you're really just storing memory addresses in the memory itself. You're storing the addresses in memory itself. Okay, and then to do the assignment, T2, we take whatever was in RBX. So this is like the classic assignment without, even if you're not using pointers, the assignment will just take some value, this value in RBX, and it'll store it in the address for T2. So remember, the address for T2 is just an offset from RBP. So after this instruction, the memory location for T2 will have 8. Questions on this? Questions on this part? All right, everybody's good on this? Does this make pointers a little easier to understand, maybe? Yes, no? Or more harder? I don't know. But yeah, I find this easier, whenever, really for anything when you're debugging, if you always kind of go down to a more fine-grained level and just kind of simulate or emulate what the machine is doing, you'll have be able to debug better, you'll be able to understand your machine better. All right, so let's assign to a dereferenced pointer now. So the next instruction that we have in our program is star T1 equals 11. Okay, so same stack frame layout, we're already here. We just executed this instruction, so now we're going to execute this instruction. So here's the instruction we're going to execute. Okay, so what assembly instruction can we use in order to store a value to an address, say, given by a register? What's the assembly instruction that will do that? Yeah. Move. What are the operands going to look like for move? Oh. Low battery. So what are the operands going to look like? Are they both going to be registers? Are they going to be memory addresses? Yeah.
Either two registers or one register and one memory address.
Yeah, it'll be one register to one memory address. And that's what, oh, you can't see that again. It keeps blowing away my. And so this is what the instruction will look like. It'll be a move from some register, so the value of some register, to a memory address. So it'll be a store. And the memory address will be given by RAX. So just the reverse of what we did to load from a dereference pointer. Here, if we want to store to a dereference pointer, we just make that address the destination. Okay, let's start out with our same state of the machine that we are before we execute this instruction. And this is the pseudocode. So we're going to get the value of the variable first. So we're going to get the value of 88, get the value of the memory at that address, and store the value of memory at that address. And then store the result into, so T1 we're trying to store into T1, store into the address given by T1, store that value into T1. All right, let's look at the actual, what the assembly code will look like for this. Okay, so first we get the value of the variable that we're going to dereference. So just like before, we get this, the value of the dereferenced variable. So T1 is the variable. T1 is the variable here. We get its value and store that in a register. So we use RAX for this. We're going to store 88 into RAX. So that gives us the value of T1. And then we store the right-hand side into another register. We use RBX. Store the other side into another register. And then finally, store the right-hand side, 11, into the address given by T1. So remember, T1 is a pointer to X. So when we run this, how will the state of the machine change? So T1 has value 88. That points to X's memory location. And we're going to store RBX, which is 11, into the memory address stored in RAX. So how will the state of this machine change when we do that, run that instruction? Yeah. Yes, 88 will be now 11. So let me go over that again. So we first take the value of T1. So remember, T1 is at negative 40 offset from RBP. We take that value, which is 88, and store it into RAX. So at this point, the machine doesn't know or care that this is an address. It's just taking the value of T1. And then we set the value of the right-hand side to a different register. So 11 is the right-hand side. We set that to RBX. And then we use this indirect store, where we take RBX, the right-hand side, and store it into the memory location given by RAX. Remember, RAX is the value of T1. It also happens to be the address of X, because that's how we set T1 originally. And after this last instruction, the address associated with X, address 88, will now be 11. Questions on this? Okay. So that's the entire example. All right. Let's see. So let me go over. All right. So okay. Okay. All right. So let me go over CodeGen 3 then. How to implement CodeGen 3. Or actually, yeah, how to implement all the whole programming assignment. Okay, so just like before, unit, local variables, assignment, those are all given to you. They're in the CodeGen handbook, code generation handbook. Hopefully you've done that already for CodeGen 1 and CodeGen 2. And just like CodeGen 2, the function-related listeners are given to you. So they're hard-coded to have the assembly translation of this simple IR program for these 5 functions. Questions on that part? Is that good for everyone in CodeGen 2? And so just as a refresher for those, I think some people are still uncertain about this, to actually use the output of your program, you make a new test case. So you make a new test case based on this. Don't just edit the same file all the time. Make a new file, copy this text, and add whatever code you're going to try out here. So remember, assign is given to you, so you can do assignment. And then add your pointer-related operations here. So I'm only going to test pointer-related operations, no branching, no arithmetic for CodeGen 3. And then you can build it like this. This is how you run your compiler. That will give you the assembly code from your compiler. Compile your assembly code like this, and run your program, just like you would for a C program. If you'd like to call the code to read or print an integer, you can copy this C file and link it with your program like this. That's what the test cases actually do. There's a hidden iolib.c file in the test cases that it links with in order to print out the integer. But you can also just use the return exit code or run the debugger to get the values. Okay, so let's go into actually implementing these 3 functions. This is what the assembly code will look like. For, let's start with reference. So I started with reference before. So this is how reference works. You use ampersand to get the address of a variable and assign it to T1. In this example, this is what the assembly code looks like. So all your CodeGen needs to do is to change only those parts that differ for different input programs. So I think we talked about this last time, but this address, this is going to be the offset of the right-hand side, and this is going to be the offset of the left-hand side. So this, you can back out a code template from this code example. The only things that are going to change for different versions of this, like let's say you had y equals ampersand of T2 or T3, then the only thing that's going to change is the offsets into the local variable array that change. Those are the only things that are going to change. So in your code, just pick out the variable name, look up in the symbol table to get the offset, and use that offset, print out that offset here. Questions on that?
If
Yeah. Sorry, say again?
We don't have to handle a user maybe a valid variable on the right side of the address.
You don't have to handle any errors. So this would be the subject of like type checking. The type checker would do this. As I was advertised, take compiler construction. It's supposed to be offered in the fall. We'll learn about how type checking works. So we can first prove that there are no such bugs in the program before we even compile the program. So that way we don't have to handle it in the compilation, the actual code generation phase. And I'm not going to test you on invalid programs. These would be undefined behavior or invalid programs. So I'll only give you variables that have been declared. But that's it. That's it. This is the code template for reference. Same for dereference. So this is reference. For dereference, we have the same idea. Here, we're taking, so for instance, this is like T2 equals star T1. So first we take the value of T1. This is the offset from of the right-hand side variable, so that's T1. It's always going to be stored in RAX, or one way to generate this easily is always stored in RAX. You're always going to do the same indirect load, and then store into whatever the address offset is for the left-hand side. Kind of make sense? So a pretty simple template. You just are literally going to spit out all this hard-coded except for the offsets. So how do we get the offsets of a symbol? So let's say we see T2 equals star T1 in our input. How do we know what the offset of T1 is? Where is this? So it's from this table, right? Where is this table in CodeGen? The symbol table, yeah. So I've given you code for using the symbol table. So I've given you kind of described it for you here, described how it gets created, and then given you examples of how to use it. So in enter assign, I've given you the code for this. And in enter assign, the way you do it is you just look up into the symbol table the name of the variable. So this is the value on the parse tree. The parse tree gives you all of the values in the actual input program. You're not going to know their names at compile time. I mean, you're not going to know their names when you write your program, your compiler, but you can just query the parse tree for those names. So get the name from the parse tree, look it up in the symbol table, and there you go. There's your offset. And this enter assign actually gives you an example of using one of these code templates. So the code template for enter assign, if we just have assign, let's say we have x equals y, then assign just does move whatever is given by the operand here. So I've already given you code to do this. And it always moves into RAX. And the second instruction always moves RAX into the memory location of the left-hand side from RBP. So this is the code template for assignment that's given to you. And you can use this as a model for writing the other assignments, because all of these are just different variations of assignment where we have extra instructions. So this is just copying the immediate or the variable value from memory into RAX and then storing RAX into the left-hand side's memory location. Reference is adding an extra instruction to compute the address of the right-hand side, and then same thing, storing it into the left-hand side. Dereference is taking the value of the right-hand side, doing an indirect load, and then again, storing it into the left-hand side. Questions on that? And finally, we have assign dereference. So assign dereference, an example of this is star T1 equals 11. And this is the code template for assign dereference. So here, the only place where you need to get an offset is here. So this is the offset of T1, the left-hand side. Store it into a register. Get the right-hand side. So this is given to you just like in an enter assign. Enter assign, you get the right-hand side like this by using my get operand function that I've given to you. And then store whatever that is, do an indirect store into RAX. So RAX holds the address of the left-hand side, and we store there. Questions on that? Yeah.
What's this program language that support 2D references at the same time? So for example, like star T1 to star T2.
No. So you mean simple IR?
Yes.
No, it doesn't support this. It doesn't support doing this. If you did, you just combine these two templates here. But the reason I do that is because assembly doesn't support it either. Well, I shouldn't say that. I mean, well, assembly doesn't have, like, you don't have this. You can't do more than one store or load in an operation. So you can't do that in assembly either. But yeah, to make it simple. So you can always re-implement this using an additional temporary variable. So we can always rewrite this as first storing star T1 into a temporary variable, and then assigning star T2 into temp. So these are equivalent programs, right? And so this kind of translation, this is very close to what your compiler is doing for simple IR, and what compilers do in general. They take more complicated or more sophisticated or higher level operations, whatever you want to call them, and they decompose them or translate them into simpler operations. So think about C or Rust or JavaScript. In one statement, you can do what you would have to write with many, many assembly statements. And so one view of programming language is that it's an abstraction of a complex set of code template, or a kind of template for, like if you have an assembly language coding pattern, the high-level language encodes that pattern with a single instruction in the high-level language. But yeah, no, you don't have to support this in simple IR. And so that's why having the grammar and formally defining the language with a grammar is so useful, because it removes cases like this. You don't have to, like, ad hoc try to think about whether you need to support this or not. You can define ahead of time what your language will look like, and you only need to account for that specific grammar, that constraint on what the input language looks like. All right, other questions on pointers? Questions on Code Gen 3 or coding in general? All right, I think that's it. I think that's it for pointers. So next time, I guess we'll just do like a review. I'll let you guys sort of drive what you need to look at for that. Otherwise, I'll see you guys on Wednesday.